Tēnā koutou katoa, haere mai, ko nisha tōku ingoa. Good morning and welcome to day 2 of NZRSA 2022. We have another day of very exciting presentations, lightning talks and demos lined up for you. And we'll begin today with our keynote by Dr. Daniel Katz at 9:30 a.m. New Zealand time. But before that, I will reiterate a few tips to make sure that we all make the most of this online platform. To ensure a smooth and enjoyable experience for all of you attending this conference, we do have a code of conduct in place. Please visit our website to read more about our code of conduct, and do ensure that you're all respectful to the other attendees on the platform. If you are having technical issues, you can click on the red live support button anytime. You can find this on the corner or top right corner of your screen. I'd like to point out that recordings of previous sessions yesterday will be accessible within this platform once the conference is over in the next couple of weeks. So don't worry if you've missed out on an interesting talk, there is a recording available. Finally, I will remind you that you can chat with other attendees and presenters in the meeting hub, which you can access on the right side of your timeline. And in the meantime, if you have any questions, please pop those into the live Q&A box. And I will do that now. I'll pause now to check if there are any questions. I don't think so. No, we're good. Okay, thanks again for being here, and I'll see you all at 9:30 when Nick Jones, the director of NESI, will come in to chair the next keynote by Dr. Daniel Katz. Thank you.
Tēnā koutou, tēnā tātou, ko Nick Jones toku ingoa, kia kaha te reo Māori. Welcome to everyone, welcome to all of us. My name is Nick Jones, I'm the director of NESI. Look, it's a pleasure this morning to welcome you back to day 2 of our annual Research Software Engineering RSE NZ meeting, and to kick off Te Wiki o Te Reo Māori, or Maori Language Week, with you all, and celebrate the last 50 years of Te Reo Māori revitalisation. And sustainability is a great theme for this morning. We can learn a lot from the activism and persistence of groups like Ngā Tamatoa, Victoria University's Te Reo Society, and Te Huinga Rangatahi, among others, who 50 years ago in 1972 presented a petition to Parliament to remove Te Reo Māori from effectively being banned in New Zealand, to being recognised and adopted as an official language of New Zealand. It would take another decade before we had Maori language education, and 13 years before Maori was recognised as an official language. So our message this morning is change takes time, and it takes the vision and commitment of individuals to sustained and collective action. Today we have the pleasure of welcoming Dan Katz to kick off the day, and with what I'm sure will be a thought-provoking rallying cry for change in research software across policy, practice, incentives, and in recognising its essential value. Dan comes from a rich heritage in research software, starting as a computational scientist at Cray, working on programming the T3E, and through NASA Jet Propulsion Laboratory and on into academia in universities and into the National Lab System in the United States. He was scientific director for the collaborative cyber infrastructure TerraGrid, which is where I think I first met him at an annual TerraGrid meeting many years ago. After a period as a fellow at the Computation Institute at Chicago and Argonne National Lab, he was NSF program director in the Division of Advanced Cyber Infrastructure. And I think there he provided some of the earliest targeted funding programs to support research software. He is currently Chief Scientist at NCSA and also a Better Scientific Software Fellow, among many other roles that he plays. All the while, Dan has been highly active in promoting the cause of research software, both through traditional forums such as a very active publication record and research collaborations, but also through leading key community initiatives, including a series of workshops, the WISPY workshops on sustainable software practices and experiences, and heavily involved in community forums such as supercomputing, and more recently, the establishment of the Research Software Alliance. So if you're involved in research software, no doubt you've come across Dan or seen the outcomes of his labours over a very long, sustained period of time. This morning, we welcome Dan to talk to us about sustaining research software issues and actions. So please join me in warmly welcoming Dan Katz to the stage for his keynote. Kia ora tātou.
Here, even virtually, it'd be even better if it was in person, but maybe next year. Yeah, so I'm going to talk about a bunch of different things related to how research software is and can be sustained, and what different groups, individuals, and organizations can do to improve the situation. But first, let me start off by talking about why we care about research software. And I think there's 3 potential answers. One of them is looking at funding. 20% of the US National Science Foundation projects over 11 years topically discussed software in their abstracts, and that was $10 billion US. 2 of 3 main Department of Energy, again, US-based exascale computing project areas are really research software, and that's about $4 billion. And when I tried to look at National Institutes of Health projects, I found about 300 million that were software development in the previous fiscal year. So there's a lot of money that's actually going into projects that build and maintain research software. There's also publications, and it's been demonstrated that software-intensive projects are a majority of current publications. and that the most cited papers are either methods papers or software papers. And really, in many cases, software is just an implementation of a method. And then finally, we can actually just ask researchers. And we've done 2 surveys, one of US researchers, US postdocs, and one of UK researchers. And we found similar results that about 90% of researchers use research software across all disciplines and all fields. About 65% would not be able to do their research without it. And about 50% develop software as part of their research. So having talked about software as part of research, where does it actually fit in? A somewhat fictitious research cycle starts with creating a hypothesis, acquiring some resources, some funding, some software, some data in order to investigate that hypothesis, actually doing the investigation, which could involve building software and creating data along the way, and then publishing the results, traditionally in a paper or a book, but potentially the software or the data are the results themselves as well. And this is really where the knowledge is. And again, this knowledge could be in the form of a paper or a book. It could be in the form of software or data or a notebook or something else more modern at this point. This then creates a cycle, and it creates a cycle because the publication process helps the investigator gain recognition, and that helps them then be able to create the next hypothesis and acquire the resources to investigate it. So software shows up here in 2 areas, 2 kinds of software. There's the research software, which is the software that's built for the research. And then there's the infrastructure software, the software that comes in at the beginning to help do the research, and the software that maybe goes out as an output of the research. Software that is not being built by the researcher for themselves, but is hopefully being used by multiple people for a different purpose. So if we explore this a little bit further, we have this idea of research software that's intended just for research. It's funded often by different funding agencies. Sometimes it's explicit, most of the time it's implicit. The PI doesn't say that they're going to build software, but it's clear that that's part of what they need to do to do their research. It's intended for immediate use by the developer, could be archived for future use and reproducibility, and it's probably dependent on the infrastructure software, that other kind of software. And so that infrastructure software is intended to be shared from the beginning. It's almost always explicitly created and funded. It's usually intended for use by at least a community and maybe by a very large community. And it's easier for the developers to hopefully be appreciated and be rewarded because it's being shared. Sometimes the developers of research software are not necessarily as appreciated or rewarded for what they've done internally. And software that's intended for research can be turned into infrastructure software, but this requires making a conscious choice, and it has consequences for the person making that choice that could be positive or could be negative or both. So if we think about this process of going from research to infrastructure, at each point or each stage where you're potentially making this choice, you have to think about your methods and your goals and these consequences. And questions that you might ask are what resources are available to help you? And what kind of work is going to be needed? So this is a nice chart that talks about the effort that's needed. When you start a project in a fluid phase, you're really working on the product itself primarily. And by the time you get to the end, you're really working on delivery primarily. You're no longer really working on the product as much. And so the skills that you need are really different. And so do you have those skills available within your team? What are the incentives for you to do this? How will success be measured? Is that something that you're interested in? And finally, how will your institution actually support you in doing this? Is this going to be something that helps you be promoted and helps you advance in your career? Or is it something that the institution doesn't really care about? Okay, so the other thing that I want to talk about with software is the idea of software collapse. And that's this concept that software will stop working if it's not actively maintained. And the reason for this is that computational science software stacks and really data science software stacks as well have a fairly common structure where down at the bottom is some kind of non-scientific infrastructure, some things like operating systems and compilers and support code and user interfaces. And then on top of that is scientific infrastructure, things like libraries and utilities that are useful for research in a lot of different disciplines. And on top of that then is discipline-specific software. And these are, again, tools and libraries primarily, but they implement disciplinary models and methods. And then finally, at the top of this is project-specific software or question-specific software, or hypothesis-specific software. And this is the software that actually does a computation using the building blocks from the lower level. And it sometimes is in the form of scripts or workflows or computational notebooks or special purpose libraries and utilities. And so the issue is that the software is building and depending on all the software and all the layers below it. And any change below may cause the software to collapse. Right? If you've built a program and it uses a library and somebody it's the developer of the library changes the API, then your software no longer will work potentially. So because of this, we can summarize research software by saying that it's the software that's developed and used for the purpose of research and can be used to generate, process, and analyze results within the scholarly process. It's increasingly essential within the research process. But it collapses if it's not actively maintained. Software bugs are found, new features are needed, and new platforms arise. This software development and maintenance is human intensive. We don't know how to automate it. We need people to do it. And a lot of the software, particularly at these top layers, is developed specifically for research by researchers. And researchers, often including those developing software, know their disciplines really well, but they often don't know software best practices. And researchers are typically not rewarded for software development and maintenance, at least not in academia. And then finally, we have the problem that developers don't match the diversity of overall society or of user communities very well. So there's a number of challenges here. I'm going to talk then about what we can do about these. And I'm going to start by defining software sustainability as just saying that the software endures. I think that really is the ultimate definition. Will the software continue to be available in the future on new platforms meeting new needs? And this can only be measured in hindsight. If we want to look forward and say that the software is sustainable, it's really a prediction. We can say the software has been sustained, but we can't necessarily say the software will be sustained. Software development and maintenance, again, requires active human effort, and human effort is kind of corresponding to money, but not exactly. We can have projects that are entirely based on human effort, things like community open source projects, and these clearly can work. And we can have projects that are entirely dependent on money, on salary, commercial software, grant-funded projects. These clearly work as well. The challenge is when you try to combine them. When you try to have a project where some people are being paid and some people are volunteering, it can be really a challenge. Effort does not quite equal money, and people are not purely rational. So I think this is the hard part is how you work in this space to make software sustainable. So again, definition, research software sustainability is the process of developing and maintaining software that continues to meet its purpose over time, which includes the software adds new capabilities as needed by its users, responds to bugs and other problems that are discovered, and is ported to work with new versions of the underlying software layers, as well as new hardware. So there's some potential solutions that we can think about in order to solve this. We can do things that reduce the amount of work that's needed to sustain the software. We can do things that increase the available resources to make that work more easy to do. Or we can do things that both reduce the amount of work needed and increase the available resources. And these solutions can be implemented at different levels by different groups. So an individual project can do some of these things, a community can do some of these things, a funder can do some of these things, and an institution can do some of these things. So if we go into this then in a little bit of detail, we can think about reducing the amount of work that's needed. So some things that we could do here are to train developers better. This involves finding or developing training materials. And this could be things like materials from the carpentries, discipline-specific materials, language-specific materials. We can also think about using best practices. And this then involves actually being able to find and develop these best practices. And so again, software carpentry in particular is a place that can do this. Incubators can do this. In the US, there's something called the Earth Science Information Partners. There's the Apache Foundation. There are others as well. So there are some things we can do to reduce the amount of work that's needed, but it's mainly doing things better in some sense with less effort. We can also think about increasing the available resources. So this means creating incentives so that people want to work on the software. We could think of things like citations that help in existing career paths, and I'm going to talk about that in a couple of minutes. We can think about how existing career paths could be adjusted so that they reward software work. And we can think about new career paths. And I'm also going to talk about that, but that one's going to be probably well known to everybody here because I'm going to talk about research software engineers. We can also increase the amount of available funding. If there's more funding available, then there's more available for particular projects as well. And this primarily relies, I believe, on making the role of software and research clear to research funders. And this could be funding agencies. It also could be industry. I think there's a variety of potential sources. And then making the case for them to increase the funding that they're providing to new software, and to make the case to them that if they do fund new software, they also need to fund software maintenance, right? That the software collapse is an issue, and that they need to make sure that it doesn't happen, at least to software that they care about. We can also seek institutional resources, and this particularly can happen if the software is considered sufficiently important to the institution, either operationally, it actually helps the institution do its job, or reputationally, the institution is known for the software. And then finally, the third part of this is to both reduce work and bring in new resources. And one of the ways to do this is really to encourage collaboration. And so if you can use the work of others rather than re-implementing a function or a package, this reduces then what a software team and its developers needs to do themselves, even without assuming that the collaborators are going to necessarily contribute to the software, which also could happen. Similarly, if others use your software and contribute to maintaining it, then you have less that you need to do. In order to make this work, the software has to be designed from the beginning to be modular and reusable. And it also has to be clearly documented and explained to potential users, even those that are in fields other than the developers. And this is often really hard to do, particularly at the start, but there can be a large reward for being able to do it successfully. The team also then has to put effort into engaging and working with this potential user and contributor community. Right? Contributors don't just come along because something's on GitHub and decide that they're going to work on it. Sometimes that'll happen, but often there's effort needed in order to encourage that to happen. So one way of thinking about this is that if you make the software findable, accessible, interoperable, and reusable, or fair, that will go a long way to at least starting this process of engagement. And then I will talk about fair in a minute as well, and that'll be the last of three kind of topics that are coming up. Okay, so 3 topics. First one is software citation. I want to talk about what has happened in the world of software citation, and this really started with the Force 11 Software Citation Working Group that ran from 2015 to 2016 that I co-chaired with Arfin Smith and Kyle Niemeyer. And what we did was initially we documented differences between software and data, trying to understand why data citation wasn't enough. And we defined a set of software citation challenges, and we published both of those things as separate documents. And then that led us into creating a set of software citation principles that was published in 2016, and I think has been in some sense the kind of the groundwork for the ongoing work that's happened in software citation. After that happened, we published this paper of principles. We decided we should create an implementation working group, and this was co-led with me and Neil Chu-Hong and Martin Fenner. Actually, it is still being co-led. We initially thought we would just have to write out a small amount of detail that would be needed in order to implement these software citation principles. And then we'd be able to coordinate research and other work going on in a lot of different areas, and to work with communities to actually implement these principles. And these communities would just be eager to do this, and they would just need a little bit of help to make this happen. We quickly realized that this small amount of detail wasn't actually small, and that scattered progress wasn't sufficient, and we aren't actually addressing any of the underlying challenges. So we wrote another paper that was called Software Citation Implementation Challenges to kind of lay out exactly what we needed to do. And we defined a set of technical challenges that included the complexity of software types and identifiers, where to store metadata, things like that. And we also then looked at social challenges where we need groups to work on implementation and context. And these groups could be disciplinary communities, publishers, repositories and registries, indexers, funders, and institutions that all needed to come together and run pilots to establish norms that would help the community move forward. So in response, we actually created a number of task forces. One of these was a guidance task force that wrote 2 checklist documents for paper authors who want to cite software and for software developers who want to make their software citable. I guess this is a good point to point out that I have a DOI at the bottom of the slides, and maybe somebody can put that into the discussion for the attendees if they haven't. And then all these links will be easily clickable if you want to get further details on any of these things. We also created a metadata task force called, we called Code Meta, that was following an existing project called Code Meta, which was aiming to look at metadata for software and to build a crosswalk of metadata standards, and then to develop another standard that could describe software based on all these crosswalks, kind of as a union of them. The task force updated the Code Meta standard, and it described everything in Code Meta using schema.org properties. And it's trying to move Code Meta now into a community group that would support basically schema.org properties for software. We created a registries task force, and this task force developed a best practices document, 9 best practices for research software registries and repositories. So for registries and repositories that want to hold software, what should they do? And the community that worked on this document is now continuing, and it's called SciCodes. It's a consortium of scientific software registries and repositories. And if you're representing a registry or repository and want to join, I think they'd be very welcome to have more people. We created a journals task force, which has been working with publishers to provide generic guidelines for journals and conferences to then customize and provide to their authors with community accepted languages, an example. And so this was a paper that we published last year with these generic guidelines. And we worked with an organization called Chorus that's basically a community organization of publishers to create for them to create a software citation policy index so that anyone can see what publishers have, what software citation policies, and we can also update this annually. We're also working on publication processing. And so I've learned that it's relatively easy for a publisher to say to an author, this is what you need to provide for a citation for software. It's much harder for that publisher then to have that information move through their internal or contractor system that actually does the back-end work, and then move on to the indices like Crossref or DataCite in order to make sure that that software is actually captured in the index. And when somebody's developed software, they can see who cited their software or how many people have cited their software. We're working on a paper on that now, and hopefully this will be done in another month or 2. And again, this will be kind of an internal paper intended to help journals handle this process better than they do now. We also considered an institutions task force, thinking of institutions as places where people work, and with the goal of affecting policy and practice. Like, how do these institutions encourage software citation? How do they use software citation information in hiring and promotion? We thought we could collect and share examples and help form communities. But we didn't really get enough interest to actually get this going. And so if anybody is interested in this, please let me know, and I can kind of put you in touch with others, and we can see if we can build up enough interest to start this. We've also been thinking then about, given the progress in all these different task forces, what else makes sense to do, and who can do it? Where do we go from here? We had a workshop about a month ago on software citation that was intended to assess and plan these next steps, and there should be a report coming out in the next couple of months to talk about this and where we are now. Okay, so next thing I was going to talk about is research software engineers. I'm not sure if I'm going to say anything here that this RSE conference attendees don't know, but maybe I'll go through some things a little more quickly than I would for a different audience. So if we think about research software, As we talked about before, a significant fraction of this is developed in research. And we have this issue that researchers and faculty generally don't know good software practices. And software engineers generically don't know and understand the research context. We have students and postdocs who maybe know how research works, but they don't know good software practices, and even worse, they don't stick around. So what happens to the software after they've left? Some postdocs do stay, and they often join staff at universities. Sometimes they're officially staff members, sometimes they're just considered postdocs for a very long time. And I would say that they're unofficial staff members in that case. There is also, though, staff that has an understanding of research as well as software engineering skills. And at this point, these things usually develop through somebody's career. We don't really have training that teaches somebody how to do this right now. So it's worth then thinking about this idea that comes from James Hetherington. Sorry, took me a second to catch that name. Where we could distinguish between the craftsperson and the scholar. And we have this idea that there's a scholar is a researcher who's driven to understand things to their fullest capability. They find intellectually demanding problems, and they work on a topic until they understand it sufficiently, and they pass on that understanding through teaching. We also have the craftsperson, who is driven to create and leave behind an artifact that really represents their efforts in the field. These are folks that feel painful when something that they've made is fragile or ugly. They prefer to make things that explain themselves. And this kind of work requires patience and pride in doing a job well. Scientific software requires people who combine the best of both these roles. And I just want to point out in the link at the bottom that this is from a blog post in 2012 as the RSE movement was starting and the idea of RSEs was starting. And this actually started in this collaborations workshop in 2012, where a group of people got together and they realized that there were already a bunch of people doing this kind of work, but they didn't have a common title. And in fact, there were 194 different job titles of the folks at UK universities who were in this workshop and in this breakout session talking about this. They decided that research software engineer was a title that everybody could rally around. They also realized that there really wasn't any community for all these people. And so they decided that associations or societies would be a way of bringing people together. And then we had the fact that this was not a profession. And so there was the idea then in response to creating career paths and structure. So thinking about what is a research software engineer, again, this is probably overkill for folks here, but we have software engineering, we have research, we have software engineers, we have researchers. We have researcher developers as well, who are kind of sitting somewhere in some space in the middle. And then we have RSEs who are really kind of more central in some ways. And there's not a particular place that RSEs sit. They really are sitting in some space in between these things. And there's a variety of different kinds of RSEs, some more focused on research, some more focused on software engineering, but really all having some aspects of both. So the RSE movement's been going on now for 10 years, again, born in the UK. In 2013, when the UK RSE Association formed, it had about 50 members. Now it's a society. It's funny. I think that this number that I have is a bit out of date. I think it's actually getting close to 1,000 dues-paying members now, and more like 4,000 members overall in the community. There also are associations and societies that have formed in Belgium, Germany, the Netherlands, Nordic countries, Australia, New Zealand, and in the US. US RSE now is up to about 1,300 members, which I'm very happy with. And there's also new associations now forming in parts of Africa and Asia. And these associations then work on local issues collectively, and they can also coordinate and work together. And so we're starting to cover some portion of the world with red areas, and hopefully we will continue to grow and cover more of the world as we go on. There's a number of advantages to RSEs, and again, you probably know this already, but maybe listing these will be useful for you to talk to your management or to others. One thing is that RSEs provide better software and more mature project management aspects and structure. RSEs understand team organization, work organization, software organization, and coding practices, and this then leads to better, more sustainable code and more effective group coordination. RSEs can provide institutional memory. As research software becomes more important and complex and costly, this expertise is valuable, and RSEs typically have longevity beyond individual projects and students, and they can be mobile across domains and can translate knowledge or artifacts across different communities. RSEs help build community expertise as well. Typically, RSEs work on a series of grant-funded projects, and these projects have a shorter duration than staff careers. And so my experience has been that RSE groups tend to move towards some kind of matrix management, where you have a principal investigator access that changes over time and is funded by projects. And then you have a group manager access that's fixed and funded by either some kind of overhead or tax on projects or institutions. And this then lets the principal investigator make sure that the RSE is working on their project, and it lets the group manager make sure the RSE is working in there, is building up skills and is being promoted in their career and is able to work with others and communicate with them. This then overall kind of leads to a pool of experts and expertise, and this then can also welcome others that have shared interests, whether or not they are titled as RSEs. Okay, and then the third thing I'm going to talk about is FAIR for research software. So the FAIR principles, I hope probably most people have heard of. This started with the FAIR Guiding Principles for Scientific Data Management and Stewardship in 2016. And they're defined as a set of principles to ensure that data are shared in a way that enables and enhances reuse by humans and machines. And there's then a set of findable, accessible, interoperable, and reusable principles. One thing that's worth looking at here is that a number of these principles start with the term metadata, with meta in parentheses, which is a shorthand for saying metadata does this as well as data does this. And so you can see the idea of data is really embedded in these principles. If we want to think about FAIR for objects that are not data, we have the fact that the FAIR principles at a high level are intended to apply to all research objects. And this is both those that are used in research and those that are research outputs. This is kind of my equivalent of research software and infrastructure software. Again, this text in the principle says metadata, which is shorthand for metadata and data. And these principles are actually applied through dataset creators and through repositories. And these two entities collectively are responsible for creating, annotating, indexing, preserving, and sharing datasets and their metadata. This assumes a separate and sequential creator role and then a publisher role, where the creator is the person that creates the dataset, the publisher is the repository that makes the dataset and the metadata public. If we think about objects that aren't data now, they can often be stored as data, but they're not just data. Again, software as an example. The high-level goals of findable, accessible, interoperable, and reusable are pretty much the same for data and other things, but the details of these and how they're actually implemented depend on how these different objects are created and used, how and where the objects are stored and shared, and how and where metadata is stored and indexed. And so there's work that's needed to define and then implement and then adopt principles for non-data objects. Again, the idea of the FAIR principles was that they would apply to all digital objects, but in practice, it doesn't quite work that easily. The FAIR Practice Task Force from EASC in 2020 created 6 recommendations for the implementation of FAIR practice, and the 5th of those was to recognize that FAIR guidelines require translation for other digital objects. And the French National Committee for Open Sciences, Free Software and Open Source Project Group in 2019 made a recommendation, a set of recommendations, and the second one was to make sure the specific nature of software is recognized and it was not considered as just data, particularly in the context of discussion about FAIR. And so there's a group of us that's focused on the adaptation and adoption of the FAIR principles to research software. So again, thinking about why this is important, what are the differences? Software is data, but it's not just data. Software is executable, while data is not. Data provides evidence, while software provides a tool. Software is a creative work. Scientific data often are facts or observations. And this leads to different licenses that are appropriate for software versus data, and different copyright practices as well. They're treated different legally. And software suffers from collapse, as I mentioned before, whereas data suffers from bit rot. And software also suffers from bit rot, but that's not the major issue. Collapse is the major issue for software. The lifetime of software is generally not as long as that of data. And maybe one of the biggest issues is that for open source software in particular, we don't have this natural sequential creator and publisher process. And there is really no natural publisher. There's no kind of archival repository that software creators feel like they need to use. They have different things they use, but they're not exactly publishers, and I'll talk about that more in just a second. So again, FAIR for Research Software was a working group that defined a set of consensus FAIR principles for research software quite recently. It was led by 9 of us that you see here. I think, I believe Paula is actually on this at this meeting as well. I'm not sure if anybody else is. And we did this under 3 different organizations because we wanted really to build community consensus around what we were doing. So we worked under Force 11, the Research Data Alliance, and the Research Software Alliance. We first defined research software, and we defined it as including source code files, algorithms, scripts, computational workflows, and executables that were created during the research process or for a research purpose. There is also additional software, things like operating systems and libraries and other things that are used for research, but they weren't created during or with a research intent. And so these should not be considered research software. They should be considered software and research, was what we said. But having said that, the differentiation varies between disciplines. So if you are a computational chemist, then your operating system is software in research, but it's not research software. If you're a computer scientist that works on operating systems, your operating system probably is research software, and it's no longer just software and research. So there's not a clean break here. It depends on what you're doing. Over a period of about 2 years, 18 months to 2 years, we ended up coming up with and publishing a set of FAIR principles for research software as an RDA recommendation or standard. And what we ended up saying, I'm going to show here and just talk about very briefly. But I want to point out as I do this that things that are in italics here are things that are significantly different than the FAIR data principles, and things that are not in italics are fairly similar. So you can see that there are things that are similar and there are things that are different. I'll say that one thing that happens immediately is that rather than using this metadata term with meta in parentheses, we have to explicitly talk about software and metadata separately. And in particular, the differences here, though, are to think that software has different characteristics than data. In particular, it has levels of granularity that are different than data, from a line of code to a file, to a version of code, to a project, to maybe a set of projects. And the different versions of the same software have to have different identifiers. In terms of accessible, the accessible principles for software are almost the same as the accessible principles for data, other than, again, some language changes. For interoperable, there are really pretty dramatic changes. And the reason for this is that it's not really completely clear what interoperable means for data, and it's even less clear what it means for software. So we decided to pick a definition, and it's not necessarily the only definition, but it's the one that we could get consensus around. And it says that software interoperates with other software through exchanging data and or metadata, or through interaction via APIs described through standards. And so this is what we mean by interoperable software in the context of FAIR. And for reusable, we also have some changes. The main one is actually a definition change, which is that software is usable initially, meaning you can execute it. And when you talk about reusing it, that can mean a bunch of different things, from that you can read it and understand it, the source code, to you can modify it, to you can build upon it, or you can incorporate it in other software. Yeah, so that's where we are. We published these principles in I don't know, May or June, fairly recently, and I think we're more or less done with our work at this point. So having said that, there are other things that are important. There are questions about governance. What do these principles actually mean? If somebody has a question, who do they go to? And what if it turns out that some of these principles are not exactly right? We've turned this over to the RDA Software Source Code Interest Group to handle these things. There is a survey of adoption guidelines we've done, to understand how the FAIR principles for research software can be adopted. And we've also done a study of adopting organizations to see what are people actually doing at this point. Are there things that you can learn from other organizations that you could bring to your own organization? And then finally, well, almost finally, FAIR exposes a bunch of ecosystem gaps, particularly related to metadata, archiving, and versions. As I said before, this creator and publisher sequence doesn't typically apply. Where metadata is stored is not really obvious. It could be in the code repository for open source, but then what do you do for closed source? It could be in an archival repository if the software is in an archival repository, or it could be in a registry if the software is in a registry. Where is code actually made available and archived for a long term? GitHub and GitLab are not archival. Registries are not archival. Repositories like Zenodo are. Software heritage is. And then there's the fact that different use cases need specific versions or the latest version or all versions. And it's not completely clear how FAIR handles that. The other issue is that there's a lot of work beyond FAIR. Right? FAIR is findable, accessible, interoperable, and reusable. It isn't high quality. It isn't correct, bug-free. It isn't reproducible. It isn't even open. So there are all these other characteristics that I think are also important to address beyond FAIR, but FAIR is a good starting point. Okay, so having gone through those three things, then what can we do? I want to start by talking about engagement in software and ask about why volunteers or collaborators choose to put effort into a software project and how can we engage them. I think the definition that I like for engagement is intrinsic motivation plus extrinsic motivation plus support minus friction. And you can think of these things in intrinsic motivation, meaning self-fulfillment, altruism, satisfaction, other things that happen inside of a person. Extrinsic motivation are things like a job, reward, recognition, influence, relationships, community membership. Support is the ease and relevance and timeliness and value. And friction is the technology and the time and the access and the knowledge that make it hard to do some of these things. So I'm going to actually abbreviate these things as IM, EM, S, and F in a couple more slides. So just to remind you, intrinsic motivation, extrinsic motivation, support, and friction. So projects then can do things like using GitHub for development. This is a way of reducing friction by using a known technology. Rather than using a different platform. They can provide a template for issues and guidelines for good pull requests. This also can reduce friction by providing knowledge of how to work with the project, and it can increase support by using the means of actually working with the project and doing this. It can provide a code of conduct and a welcoming and encouraging environment. And this can increase extrinsic motivation by helping to develop relationships in a sense of community. It can provide good first issues. This can increase intrinsic motivation and support by creating easy wins, things where people can come in and do something and be successful and then want to do more. Project can add contributors to a list of authors who are cited when the software is used. And this can then increase both intrinsic motivation as well as extrinsic motivation by recognizing the accomplishments of the contributors. And you can highlight examples of how the software is used, and that helps people that really can feel like they're actually making a real contribution to science. And the last thing is that you can ensure that the project is diverse, and you can try to highlight diverse elements of the project and of the community. And these can increase the extrinsic motivation and decrease friction by strengthening the community and by giving people examples that they can understand. We can also think of a progression of engagement, and the idea here is to plan for a progression of types of engagement. Right? That having a public repository and doing some promotion and having an open source license creates the opportunity for people to discover the project. And then having a mission and vision and communication channels in the README helps create a first contact. Once that contact has happened, you can use personal invitations, contributing guidelines, and a code of conduct to help move that to participation, and so forth. And the idea is to move from participation then to sustained participation, to networked participation, and ideally to move some people to leadership. So that overall, the community has an expectation of running the project, of buying into it, of being part of it, of co-owning it. And really, so the question here is to consider what are these things that a project can do to encourage a potential contributor to move from one level to another. Communities can think about systematic change. They can support incentives and citation, and these are disciplinary communities, for example. They can support RSEs, see this as a valid career path, and include training to help with this. They can support software work, things like offering prizes, having conference sessions that are dedicated to software and to research software specifically. They can encourage fair software. They can communicate. They can talk about the community as a whole, about the software that the community has built, about needs, where there's a need for more software, and gaps, areas where maybe software doesn't match as well as it should. And they can collaborate, which is a way of encouraging different community members to come together and develop and maintain extensible community software projects. Funders can work also towards systematic change. They can support, again, incentives and citation. They can support RSEs. They can see this as a valid career path again and include supporting training for RSEs. They can fund more explicit software development. They can also require that software that they are funding is going to be fair. They can require open software by default while allowing exceptions when that makes sense. They can require proposals to talk about sustainability. So people that are writing proposals to develop software have a plan, maybe a software management plan for what they're going to do after the funding ends to keep this investment going, to keep the software going. They can accept that funding new software implies an obligation to fund its later maintenance. And they can also then support research in measuring the impact of these changes and actually improving these changes. And this is an area I think that very few funders are really doing in a systematic way today. This can include collecting and analyzing software work being funded. So I'll just point out at the beginning when I talked about understanding the role of research software, I pointed out some evidence of 3 different US funding agencies and how much software work they funded. It's almost impossible to really gather that data though. And I don't know of any way to do it well for the US funding agencies. I don't know of any way to do it well for any other funding agencies. So I would love to see some ways of actually doing this. Institutions, again, can look at systematic changes or systemic changes. They can, again, support incentives and citation. They can provide an RSE career path within their institution through usually an HR organization and its changes, maybe through a computational center like NESI, maybe through an IT organization, maybe through a research organization. They can count and reward software work in hiring and promotion, not just for RSEs, but also for faculty and for other staff. They can support fair software. They can make that something that they ask for. They can encourage open software themselves. They can support key packages as institutional products and take pride in doing that. And they can create an open source program office, or an office at the university that encourages open source, encourages software overall. And they can also ensure that their technology transfer office, if they have one, is actually measured on transferring technology, including via open source, and is not measured on making money, which unfortunately is the case for, at least in the US, a number of technology transfer offices. So with that, I want to wrap up. I want to thank a number of people, Arfin Smith and Kyle Niemeyer, Neil Chu-Hong and Martin Fenner for co-leadership and software citation activities. Neil, again, Simon Hetrick, James Hetherington, Rob Haynes, Ian Cosden for a number of interesting RSE discussions. A bunch of people for co-leads in the Fair for Research software work. A bunch of different colleagues for a lot of different discussions over time on this. The Better Scientific Software project that gave me a fellowship in 2017, I believe, to pursue some parts of the citation work. And if you're interested, you can follow my blog, which I haven't been writing very much of, or tweets, which I've been doing a lot more of. And with that, I'm going to stop and see if there are questions or things people want to discuss in the next 10 minutes.
Kia ora, thank you. Kia ora. Thank Thank you, Dan. Sorry about that. I had you in full stereo, so I really wanted the full immersive experience, but that was a little bit too much feedback, really, wasn't it? Look, thanks for a great talk. You really covered a lot of ground there, and I loved some of the imploring, especially the do both around reducing the amount of work and increasing the available resources, and covering off the software citation, career paths, and fair topics in a great deal of richness, if not time to truly give them their full worth. A lot around building community and engagement, and I thought that was really fascinating. It was great to see Abigail's work on Work Open and Lead Open. And I think you're quietly and with great humility looking at that overall system and thinking about the change required within it. It's amazing how many little areas and back alleys you've been able to discover through all your experimentation and reframing. So some really interesting work there. Thank you.
Yeah,
I have got a couple of questions here, so we'll go to those in a second. There's a live poll there, Dan. So I just took a quick poll of the audience to see how many people were aware of the Fair for Research software, and so that just gives you a little bit of an insight into who's in the room and their background around this, particularly around that Fair for Research software topic. So let's go to the live Q&A, and I'll start with Alexandra. I'll just move my scroll on down. I think you were early on in there, Alexandra. So Alexandra Palak talks, who I'm sure you're familiar with, notes great talk and asks regarding the work with journals. What has been the response so far? Any major roadblocks that the publishers bring in? And I'm assuming this is where you were talking about that sort of pipeline of citation indices, metrics, and what you're trying to do there. Hopefully I've got that right, yeah. Alexandra.
Yeah, so sorry, I'm just trying to see. Yeah, so I guess that's primarily in the context of citation at this point, but there's starting to be interest in FAIR as well from the journals. I would say that the thing that's been interesting to me is that I ended up starting to work with Shelley Stahl from the American Geophysics Union, and it turned out that she was really exactly the right connector, who was interested in software citation and also had great relationships with a number of publishers. And so she was able to really bring in a number of the folks that turned into our roughly 20 publisher working group that meets monthly. We just had our most recent meeting was on Friday last week. And so the paper that we wrote has, I think, 17 or 18 of those publishers as co-authors. And that was really very intentional to get them to buy into this concept enough that they would want to claim it as something that they were doing. And so I think the uptake really has been very good at this point in terms of the idea. There's additional publishers that we haven't reached out to, but we're trying to work through different publisher groups as well. So Shelley and I and others have been giving talks in publisher forums, which has been a kind of another interesting example of another, what to me has been a kind of a back corner of the scholarly world. It's been interesting to put a little light in from my point of view. So I think overall I would say publishers in general want to do the right thing. Sometimes they have different definitions of what the right thing is, but if they see the community moving in some direction, they want to support the community and make their systems do what the community wants in a general sense. Nick, you're muted, I think.
Thanks, Dan. I'm having a little bit of trouble with sound my end, so I caught most of that, but I'm sure our audience caught all of it. Look, I'm back here with my mic, so that's great. I can come back in and just at least prompt the next question. So I wanted to hand over to Hilary Oliver, and he asked perhaps an unfair question. I'm not sure if we meant to have a drum roll just there. So was FAIR a set of principles chosen primarily to make a catchy acronym? And so this is a question with a bit of levity. But I guess he's sort of there prompting the question around, it's missing some other important principles perhaps.
No, I don't think there's any levity. I think it's a very serious question and a very interesting one to try to understand. So I was not involved with FAIR when it started. Initially, I kind of came in around, I don't know, I was in a workshop in 2015 as things were kind of wrapping up. But my understanding is that it was a bunch of people that came together and tried to talk about what they wanted to do, which was how, again, to make data um, more useful and more usable by both humans and machines. And they came up with lots of ideas of how to do that, and then they started grouping those, and they came up with FAIR as a catchy acronym that reflected the things that they thought were most important at that time. I think almost immediately after FAIR came out, other people started pointing out the things that were not included, and I think there's no question but that there are other things that are not included. When I talked about some for software, I think there are some for data as well. And so I think the answer to this is, because FAIR is a catchy acronym, it actually has gotten a lot of uptake, I think, because people remember it and because funders and policymakers can say that they're doing something, and it's something that makes sense to them. And so even though it's not complete, I think it is a good starting point, and it's now really up to us to continue on past there. There are obviously other examples of other acronyms that have come up since then. There's CARE, there's DOME, there's a number of other things. It's not clear that any of these are quite getting the same buy-in, and I don't really know why not. At this point, there are a number of other equally important things to do, but maybe we just need to push on FAIR and get it to be accepted, and then try to move on to the next thing rather than trying to do too many things at once.
Kia ora. And I think that in particular, when you get into care, it's an area that's of particular interest locally with our considerations around things like Indigenous and Maori data sovereignty and safe algorithms and those sorts of things. We've got time, I think, for a couple more questions. So you did note Paula is in the audience, and so she just wanted to thank you for all the work. And I'm sure she's thanked you before and will thank you again. She was asking, could you mention one or two victories you're most proud of leading the change on?
Yeah, so I think I would say the work that we've been doing with publishers and citation, I think is definitely one of those at this point, because it really is starting to have an impact. And I feel like it was an example of, at least for me, I feel kind of a strong sense of accomplishment, because it's not something that I think I would have been able to do a couple of years ago,